Welcome back. In this video, we are going to solve problem 9-43 that is taken from chapter number 9, Stress Transformation, and book name is Mechanics of Material by R.C. Hibbler. So statement is the nose wheel of the plane is subjected to a design load of 12 kilonewton. Determine the principal stress acting on aluminum wheel support at point A. So you can see this is the plane wheel that is subjected to 12 kilonewton load acting on nose wheel at this point, and this is the wheel support. So you have to find the principal stresses at wheel support at point A. And from here you can see this is the cross section of this portion at this portion. So 20 millimeter plus 20 millimeter, so total height is 40 millimeter and width that is in this direction is 30 millimeter, and this is point at mid we have point A. So let's start with the solution. So first step is that if you cut this wheel at point at this portion and draw the free body diagram. So I will first draw the free body diagram. Let this is the wheel there, and this is the shaft of the wheel. Let me extend it. Okay, and then you have the wheel support that is like this. Clear? Okay, and then you have, so when you cut it at point A, you will be having a normal force that will act on this surface. Let this normal force is represented as N, and you will be having a shear force that will act over this surface. This will be the shear force in this surface. Clear? And you will be having a movement as well. This movement is M. And you can see this, there is a load of 12 kilonewton that is acting on nose of the wheel. Clear? And distance between this nose of the wheel and this point A is 150 millimeter. So this distance is this distance, and this point A distance, this distance is 150 millimeter. So we will find these reaction forces and moment by using equation of equilibrium. So first equation of equilibrium is that sum of all forces along y direction must be equal to 0, and here we will take the y direction in this direction is taken as positive. Because why we are taking this, so you can see this is the new transformed portion. So we are taking the all the forces in this direction as y direction, and this direction as taken as x direction. Okay, so now you can see that this force N which is acting in the opposite to that, so it will be minus N, and you can see from here that this is point, so this is point A, and if you draw a horizontal a line, so this angle is 60 degree, so remaining will be 30 degree. And you can see that if I draw a line parallel to this line which is 30 degree, making 30 degree with this vertical line, so it will be like this. Clear? So we will resolve this 12 kilonewton into two components. So one component will be in this direction, in x direction, and other one will be this, and this angle will be 30 degree. Why? Because you can see that this is the vertical line, so this is a vertical, this is the line, this is, so that this angle will be also 30 degree. So this component will be 12 into cos of 30 degree, and this component will be 12 into sine of 30 degree. Now sum of all forces along y direction must be equal to 0, and force in this direction is taken as positive. So N, and this component is in positive y direction, which is 12 cos of 30. So I will write plus 12 into cos of 30 degree is equal to 0. So from here you will get N will be equal to 10.392 kilonewton. Similarly, you can find this shear force. So for that we will apply equation of equilibrium, that sum of all forces in x direction is taken as uh, is 0, and force in this direction is taken as positive. So you can see this shear force in this direction is positive, and the other component, this is in negative direction. So I will write V minus 12 into sine of 30 degree is equal to 0. So it means that shear force comes out to be 6 kilonewton. Now we will find this moment. So we will find this moment by using equation of equilibrium, that sum of all moments about point A is equal to 0, taking the counterclockwise moment as positive. So you can see this moment about point A is counterclockwise, so it will be positive, and the other moment about this point A is, this is the perpendicular distance, which is 150 millimeter, and this is the force, and this is producing clockwise. So their sum must be equal to 0. So m minus 12 into 150 millimeter, which is in meter is 0.105, is equal to 0. So from here you will get moment will be equal to 1.80 kilonewton into meter. Now you have this normal force, you have shear force, and you have moment as well. So you can see that due to this normal force, we will have a normal stress. Due to this force, shear force, we have shear stress. And due to this moment, we will be having a bending moment. So this is the combined loading. So for normal stress, I will write it normal stress. So normal stress will be equal to sigma, and that is equal to N over A, which is the normal force, plus minus M into C divide by I, or you can also write m into y divided by I. Okay, as this normal force is toward this surface, so it will be in compression. So we will take this stress as compressive stress. So in compressive stress we can write it as minus. Okay, so N is 10.392 divided by area. So cross section is given as 20 by 30. 20 is height and 30 is width. So 20 millimeter in meter is 0.02 and 30 is 0.03 meter. Clear? And you can see from this cross section, this is point A, so this will be the neutral axis. So at this point A, we have this C is distance from neutral axis till topmost, or we can also correct it and we can write it as y, m into y divided by I, and y is distance from neutral axis till any point. So this is y. So here y is equal to 0. So it means that stress due to bending moment will be 0, and we will only have this compressive stress. So sigma will be equal to 8.66 megapascal. Also you can see n is kilonewton, so I will multiply with 3, and this will be minus, or you can say 8.66 megapascal, and that is in compression. Negative sign means it is in compression. Now we'll find the shear stress. So we know that shear stress at point A is equal to V into QA divided by I into T. And what about QA? So QA will be equal to Y dash bar into A. So this is the point A. So above point A, this will be the area, and this area is 30 millimeter into this 20 millimeter. One more thing is that this total is 40 millimeter. So this is 20 each, so 40 millimeter. So I will also correct it over here that this is 0.04. Okay. So y dash into A. So y dash is distance from neutral axis till mid of this section. So till mid of this section, this distance will be equal to 10 millimeter. So this will be 10 millimeter, and that is equal to 0.01 meter. This will be y dash bar, and this area will be equal to 30 multiplied by 20. So I will write it. Y dash is 0.01 and area is 30 millimeter, which is 0.03, and width is 0.02 meter. Clear? And we have V value, which is this one, 6 kilonewton. So you can just put it 6 into 10 raised to power 3 multiplied by QA, which is 0.01 multiplied by 0.03 multiplied by 0.02 divided by thickness. So thickness, you can see this is the thickness. So this thickness is 30 millimeter. So I will write 30 millimeter in meter. It is 0.03. And what about I? So I for this cross section about this neutral axis. So this is its width and this is its height. So width is 30 and height is 40. So for cross sectional area of rectangular, we can find it 1 over 12 b. B is 0.03 and h is height is 0.04 whole cube. Clear? So you can find the shear stress. So when you calculate it, will be 7.50 megapascal. So if you draw the state of stress on the element, so let this is the element. Clear? So you can see sigma y, which is this one in this direction. This was y, so this is sigma y, and that is 8.66 in compression megapascal. In this direction we have taken x, so sigma x is not available. Sigma x is equal to 0, so there is no need to represent it. And tau of xy is this one, which is the tau a, which is tau of xy is equal to 7.50 megapascal. So we want to find the principal stress. So we know that principal stress sigma 1 comma 2 is equal to sigma x plus sigma y divided by 2 plus minus sigma x minus sigma y divided by 2 whole square plus tau of xy whole square. So put the value 0 minus 8.66 divided by 2 plus minus 0 minus plus 8.66 divided by 2 whole square plus tau of xy, which is 7.50 square. That will give you sigma 1 comma 2. So when you add it, sigma 1 will be equal to minus 8.66 divided by 2 plus under the root 8.66 divided by 2 whole square plus 7.50 whole square, and that will be equal to minus 4.33 plus 8.66025. So when you add them, you will get sigma 1 comes out to be 4.33 megapascal. Similarly, you can calculate sigma 2, and sigma 2 will be equal to minus 8.66 divided by 2 minus under the root 8.66 divided by 2 whole square plus 7.50 whole square, and that will be minus 4.33 minus 8.66025, and from here you will get this as minus 13 megapascal. So your principal stress sigma 1 is 4.33 megapascal and sigma 2, which is minus 13 megapascal. So these are the principal stresses that is acting at point A of the wheel support. And that was all about this problem 9-43. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. In this video, we are going to solve problem 9-34 that is taken from chapter number 9, Stress Transformation, and book name is Mechanics of Material by R.C. Hibbler. So statement is determine the principal stress and the maximum in-plane shear stress that are developed at point A in 2-inch diameter shaft. Show the result on element located at this point. The bearing only support vertical reaction. So you can see this is the shaft that is supported by two bearings at the end. There is a 300 pounds load acting at a distance of 36 inch from this end and two horizontal forces 3000 pound each in opposite direction. So at this point A, we have to determine the maximum our principal stresses and maximum in plane shear stresses and we will show the result on element located at this point. So let's start with the solution. So first step is that if you remove this bearing at this location, let this is 1, this is 2 point, so there will be reaction force which is represented as R1, and if you remove the bearing number 2, so you will be having reaction force which is R2. We will find this R1 and R2 by using equation of equilibrium. So first equation of equilibrium is that sum of all moments about point 1 is equal to 0 and taking the counterclockwise movement as positive. So about this point 1, the first movement will be 300 pound into perpendicular distance is this 36 inch and it is producing clockwise, so it will be negative. The second movement about this point 1 is R2 into perpendicular distance is 48 and this is producing counterclockwise movement, so it will be positive. And the sum of both movement about point 1 will be 0. So I will write minus 300 into 36 plus R2 into 48 is equal to 0. So from here we will get 48 R2 will be equal to 300 multiplied by 36 and R2 will be equal to 300 multiplied by 36 divided by 48, and when you calculate it you will get R2 is equal to 225 pounds. Clear? So R2 is 225 pounds. Now we'll find R1, and R1 can be obtained by using equation of equilibrium that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So R1 is upward, R2 is upward, both are positive, and 300 pound force is downward, so it will be negative. But their sum must be equal to 0. So R1 plus R2 minus 300 is equal to 0. So from here we will get R1 is equal to 300 minus R2. So R1 will be equal to 300 and R2 is 225 pounds. So we will get R1 will be equal to 75 pounds. Now we have R1 and R2. So what we will do is that we are interested to find out the principal stresses at point A. So for that we will cut this beam at this clear at point A, and when we draw the free body diagram of this, so this is point A clear, and this here this is point 1 where we have R1, and this R1 is equal to 75 pounds. You have a horizontal force of 3000 pounds as well. The distance between from point 1 till point A is 24 inch clear, and when you cut it at point A, so you will be having a shear force that will be acting a downward V. you will be having a normal force that is perpendicular to this surface, that will be N, and you will be having a moment in counterclockwise, that is reaction moment. So let this is your point O. So what we will find this V, M and N by using equation of equilibrium. So first equation of equilibrium is that sum of all forces in x direction must be equal to 0 and force in this direction is taken as positive. So 3000 pound force which is in opposite, so it will be minus 3000 plus this N is in positive direction, their sum must be equal to 0. So from here you will get this normal reaction force will be equal to 3000 pounds. Similarly, you can find this shear force V by using equation of equilibrium, that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So R1 which is upward, so 75, and V which is acting downward is equal to 0. So V is equal to 75 pounds. Now we will find this moment, and for moment we will apply equation of equilibrium, that sum of all moments about point 1 is equal to 0, point O is equal to 0, and taking the counterclockwise moment as positive. So about this point O, this moment is reaction moment which is counterclockwise, so it will be positive. About this point O, the other moment will be R1 into perpendicular distance 24, and this is clockwise, so it will be negative. And the sum of both moment will give you 0. So R1 which is 75, so 75 into 24, that is minus plus M is equal to 0. So from here you will get this moment will be equal to 75 into 24, which is 1800 pounds into inch. Now you can see that you have this normal load, you have shear load, and you have moment. So due to this normal load, tensile load, we will be having a stress, that is normal stress. Due to this shear force, we have shear stress, and due to this bending moment and this moment, there will be bending stress. So here stress will be, I will write stress, normal stress will be the combination of, that is normal stress will be the combination of N by A, that is tensile, so it will be positive, plus minus stress due to movement, so that is M into Y divided by I, or you can also write M into C divided by I. So difference between C and Y is distance from neutral axis till any point, while C is distance from neutral axis till the topmost. Okay, so here you can see you have a movement like this and movement like this. So due to this movement, the upper portion will be in compression. So this A point A will be in compression. So this equation will become equal to sigma is equal to N by A minus M into C divided by I. Why C? Because C is distance from neutral axis and point A lies to the topmost layer. So this is your C. Okay, so now put the value, for that we need area and moment of inertia. You can see A and I. So area of this circular shaft is, if it has a radius given as 1 inch, so area of this circular shaft is pi r square or pi c square. So pi r square, so pi multiplied by 1 inch square, 1 square. So area will be equal to pi inch square. Similarly, moment of inertia for circular rod having radius r is represented as pi by 4 r power 4. So put the value pi by 4, r is 1 power 4. So we will have only pi by 4, inch unit will be inch power 4. Now you have all the values, you can just put it over here. So sigma is equal to, here y, I will also write it here, y is distance from neutral axis till topmost layer, that is equal to c is equal to 1 inch. Clear? Put the value, n is 3000, so 3000 divided by area is pi, minus m is 1800, c is 1 divided by pi by 4 inch power 4. So when you calculate it, you will get the normal stress comes out to be minus 1.337 into 10 raised to power 3 psi, or you can say this normal stress is 1.337 KSI, and then I have removed the negative sign, and instead that I have written this stress is compressive stress or compression. Okay, so we have compressive stress. Now we'll find, due to this shear stress, we will having a shear force. This due to this shear force, we have shear stress. So we know that shear stress at point A is equal to V into QA divided by I into T. So if this is the circular shaft and this is its neutral axis, this is your point A. So QA is actually equal to y dash bar into A. So this point is A. So over the point A, we do not have any area. So A is equal to 0. So it means that QA is equal to 0. Since QA is equal to 0, shearing stress at point A is equal to 0. And again, no uh, there is no stress in y direction. So we have sigma x is minus 1.337 ksi, and shearing stress is tau of xy, which is equal to 0, that is tau a, and sigma y is also 0. So if you want to represent it on a element, so it will be like this: sigma x in this direction is 1.337 ksi, and there is no force stress in y direction and there is no shear stress, so it is like this. Now if you want to find the principal stresses, so we know that principal stress is sigma 1 comma 2 is equal to sigma x plus sigma y divided by 2 plus minus under the root sigma x minus sigma y divided by 2 whole square plus tau of xy whole square. So just put the value. Sigma x is minus 1.337 divided by 2 plus 0 plus minus 1.337 minus 0 divided by 2 whole square plus tau of xy, which is equal to 0, is whole square. So this will give you minus 1.337 divided by 2 plus under the root minus 1.337 divided by 2 whole square. Clear? And this will be sigma 1. So this square will cut with this, and this 2 will this value will become positive. So minus 1.337 divided by 2 plus 1.337 divided by 2, that will be equal to 0. So you have normal stress is equal to 0. Similarly, sigma 2 will be equal to minus 1.337 divided by 2 plus minus 1.337 divided by 2, and this will give you minus 1.34 KSI. So this sigma x is 1.34 KSI. We can also find this normal stress by using the Mohr circle. So this was the state of stress. This is minus sorry, 1.3334 KSI. There is no other stress. So we know that by using Mohr circle, if you draw the axis, vertical axis is for normal shear stress and horizontal axis for normal stress. So we have only compressive stress, that is minus. So for that we will need sigma x comma tau of xy, and other component is sigma y comma tau of xy. So here sigma x is minus 1.34 comma 0 and sigma y is 0 comma 0. So if you plot it, let this is minus 1.34, clear, comma 0. So other point will be 0. So its Mohr circle will be like this, clear, it will be like this. So here you can see that this is sigma 1, which is again equal to 0, and sigma 2 is minus 1. Sigma 1 is equal to 0 and sigma 2 is minus 1.34 KSI. So this is another way to find out the principal stresses. I have explained the both two, clear. Sigma 1 is 0 and sigma 2 is this one. Now if I represent it on a state of element, so this will be the state of stress. So your principal stress sigma 1 will be equal to 0 and sigma 2 is, sigma 1 is this one, which is equal to 0, and sigma 2 will be this one, minus 1.34. Now for in this, if you look at this Mohr circle, this is the center, and at center we have the coordinates, which is sigma average comma tau in plane. So this is the maximum in plane shear stress, and we can find maximum in plane shear stress by using this formula, that is tau max, that is in plane, clear, is equal to sigma x minus sigma y divided by 2 whole square plus tau of xy whole square. Okay, so sigma x is minus 1.337 minus 0 divided by 2 whole square plus tau of xy 0 square under the root. That is maximum in plane shear stress. Okay, so when you calculate it, you will get it as minus 0. Sorry, it will be equal to 0.668 KSI, or that is equal to 668 PSI. So this is the value of maximum in plane shear stress. And with this in plane shear stress, we have average stress. So average stress will be equal to sigma x plus sigma y divided by 2. So minus 1.337 plus 0 divided by 2 will be equal to 0.668 KSI. And that is minus. So minus 668 PSI. That is the average shear stress. You are using the Mohr circle. So for that, if you want to find the plane of maximum shear or in plane stress, so this is 2 theta s. So 2 theta s is, you can see this is 90 degree. So theta s for representation on element, theta s will be equal to 45 degree. So by using Mohr circle, you get theta is equal to 45 degree in counterclockwise, or you can see if you want to find it like here, so it will be minus 45. So theta S1, theta is 45 and minus 45 degree. But if you want to find the plane of maximum shear by using formula, so in maximum in plane shear stress, so tangent of 2 theta s is equal to minus sigma x minus sigma y divided by 2 clear, divide by tau of xy. So just put the value minus sigma x is minus 1.337 minus 0 divide by 2, clear, divide by 0, which will give you infinity. So theta is 2 theta s is equal to tangent inverse infinity, which is equal to 90 degree, and theta s will be equal to 45 degree. Clear? So you will get the same answer, 45 degree. Again, you can put it theta 45 degree in this formula. Tau of x dash y dash is equal to minus sigma x minus sigma y divided by 2 sine of 2 theta, which is transform stresses. So when you put 2 theta is 90 degree over here, theta is 45 to 2 theta is 90 degree. So you will get the transform stress at angle of 45 will comes out to be 0.668 ksi. You can just try it. It is 668 ksi, which is the maximum in plane shear stress at 45 degree. Now, if you want to represent it on a state of stress element located at point A, so this is your initial x-axis, this is your y-axis, clear. So theta is 45 degree from, so your new or transforms axis will be this one, clear. This one will be your y dash, and if you draw the element like this, clear, you have to make it straight. This is the element, clear. So your average shear stress will be this theta is 45 degree counterclockwise. So this is your average shearing stress over all the sides, that is negative, so minus, so it is like this, clear. This is average shear stress, and your average normal stress, and your average in plane shear stress will be like this one. It will be like in plane shearing stress will be like this one. This is tau max in plane. So this is the representation of in maximum in plane shear stress and the average stress, and that is the representation of principal stresses. And that was all about this problem 9-34, and I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. In this video, we are going to solve problem 9-35 that is taken from chapter number 9, Stress Transformation, and book name is Mechanics of Material by R.C. Hibbler. So statement is the square steel plate has a thickness of 10 millimeter and is subjected to edge loading as shown. Determine the maximum in plane shear stress and average normal stress developed in the steel. So you can see this is the square steel plate of 200 by 200 millimeter. This thickness is 10 millimeter and there is edge loading shown, clear. So you have to determine the maximum in plane shear stress and average normal stress developed in the steel. So we'll solve it by using stress transformation equation, and then we will solve the same by using Mohr circle. Both will give you the same answer. So let's start with the solution. So you can see this is uniformly distributed load of 50 Newton per meter. So when you convert this load into a point load, so what you will do is that you have to multiply this 50 Newton per meter with the length, which is 200 millimeter. So 200 millimeter in meter is 0.2. That will give you 10 Newton load. Clear? This is Fy. Same is the case here downward. So when you convert it into a load, so this will be Fy. This is compressive load. Same is the case is that if you convert this load into a point load, so this 50 Newton per meter into the length, which is 0.2, will give you 10 Newton load, and this is in x direction, so this is Fx. Clear? So this is Fx. Now we'll find the stress, which is sigma x, and sigma x will be equal to Fx divided by the area. So Fx is 10 Newton, clear, 10 Newton, and this area of this will be equal to this thickness, which is 0. This is the thickness, which is 0.01 meter, and this height, which is equal to 0.2, will give you this area. Clear? And this area will be equal to 0.2, which is the height, and thickness is 0.01. And when you solve this, you will get it 5000 Newton per meter square. So this sigma x will be equal to, in term of this is 5000 Pascal Newton per meter square, and that is equal to 5 kilo Pascal. So we have converted this this point load into stress. So sigma x is stress. This is, sorry, x in this direction. So this load is converted into normal stress in x direction. Same you can find this sigma y, and this sigma y, you can see this is a compressive load, so it will be minus. Clear? So minus Fy divided by the area. So Fy is minus 10 divided by, now this area is same, this is 0.2 meter or 200 millimeter, and this thickness is 10 millimeter or 0.01. So this is the area. So I will write the same area, 0.2 multiplied by 0.01, and that will give you minus 5000 Newton per meter square, or you can say sigma y is minus 5000 Pascal, or sigma y is equal to minus 5 kPa. So there is no shear stress. So from here you can see that sigma x is 5 kilopascal, sigma y is minus 5 kilopascal. There is no shear stress, so tau of xy is equal to 0. So we are going to find out the maximum in plane shear stress, and we are using stress transformation equation. So A, stress transformation equation. So we know that maximum in plane shearing stress is equal to sigma x minus sigma y divided by 2 whole square plus tau of xy whole square, and this all the terms are in under the root. So just put the value, sigma x is 5 minus 5 divided by 2 whole square plus tau of xy, which is 0 whole square, under the root, will give you the maximum in plane shear stress. So when you solve this, you will get 5 plus 5, 10 divided by 2 is 5, which is 25 square, and that will give you 5 kilo Pascal. So this is maximum in plane shear stress. Now we'll find the average shearing stress. So average shear stress is equal to sigma x plus sigma y divided by 2. So 5 minus 5 divided by 2 will give you sigma average stress, and that is equal to 5 minus 5 is 0 divided by 2. So that sigma stress will become equal to 0. Now you have this maximum in plane shear stress and average shear stress. So we will find the plane of maximum in plane shear stress. So for that we have formula, which is equal to tangent of 2 theta s is equal to minus sigma x minus sigma y divided by 2 Clear? This sigma x minus sigma y whole divide by 2 divide by tau of x y. So just put the value minus sigma x is 5 minus 5 divide by 2 and divide by 0, that is equal to tangent of 2 theta s. So 2 theta s will be equal to tangent inverse infinity, and that will give you 90 degree. So 2 theta s is equal to 90 degree, so it means theta s is equal to 45 degree. Now we'll put this theta in the equation, which is equal to tau of x dash y dash is equal to minus sigma x minus sigma y divided by 2 into sine of 2 theta plus tau of xy cos of 2 theta. So minus 5 minus minus plus 5 into sine of theta is 45, 2 theta is 90 degree plus 0 into cos of 90 degree. That will give you transform shear stress at angle of theta s. So divide by 2. So when you calculate it, you will get this as minus 5 into sine of 90 degree, which is equal to tau of x dash y dash, and that is equal to minus 5 kPa. Why we put theta in this transform equation? In order to find the direction. So if you draw the state of stress element, let this was your initial x-axis and this is your y-axis. Now at theta 45 degree counterclockwise. So let this is the 45 degree counterclockwise will be your new transform stress axis x dash y dash. And if you take the element like this, it should be like this. Clear? So you can see that your tau of x dash y dash is negative, so it will be like this. This will be your shearing tau of x dash y dash. And this is equal to tau of x dash y dash. Our maximum in plane shearing stress is 5 kPa, that is negative. Clear? And average shear stress is equal to 0, so there is no shearing stress. So this is our solution, that average shearing stress is 0 and average normal stress is 0 and maximum in plane shear stress is 5 kPa. So we use this in order to find the direction. So that is negative, so we use this. And this is the angle, which is theta is equal to 45, theta s is equal to 45 degree in counterclockwise. Now we will solve the same question by using Mohr circle. So for Mohr circle, we need this coordinate sigma x into tau of xy and other coordinate sigma y comma minus tau of xy in order to plot this. So for that, I will take a horizontal axis on which we will take normal stress, and we will take vertical axis for the shearing stress. Clear? And we will plot this sigma x. So sigma x is 5 and sigma y tau of xy is 0. Similarly, sigma y is minus 5 and 0. So we'll plot this. Let each division is of 1 kPa. So 1 plus 5 0 1 2 3 4 5. So this point is 5 comma 0, and this 1 2 3 4 5, this will be minus 5 comma 0. So if you draw a circle that is passing through these 2 points, let me draw a roughly circle. This is actually not a circle. If you draw it by using compass, so it will be like this. Clear? So from here you can see that this is the center, which is equal to 0 comma 0, and we know that this center C is 0 comma 0, which shows that this C is average comma tau of xy. Clear? So at this point, so you can see we have sigma average is 0. Clear? And this sigma average is equal to 0. Now you can see here, this is the maximum in plane shear stress at this point, in plane shear stress, and you can find it by using this r. This is the radius of circle. Clear? This is the radius of circle, so this r is equal to maximum in plane shear stress in plane. So this R formula can be, we can use for formula for R is sigma x minus sigma y divided by 2 whole square plus tau of xy whole square under the root. So put the value, sigma x is 5 minus minus plus 5 divided by 2 whole square plus 0 square will give you R will be equal to 5 kPa. So you can see this R is equal to maximum in plane shear stress. So maximum in plane shear stress is equal to 5 kPa. Clear? And again, if you have drawn this Mohr circle as per the scale, so you can see 1, 2, 3, 4 and 5. So it will be exactly at this point. Clear? Let me correct it. It will be like, it will be at till this point. This will be your in plane shear stress. Okay. Now you can see theta s is equal to this total, this angle counterclockwise. This is the point, this line is the state of stress shown. So if you want to convert it into this, so you have to take it 2 theta, this is 2 theta s. So if this 2 theta s is equal to 90 degree, this line will become a vertical line. So where we have the maximum in plane shear stress. Clear? So this 2 theta s is equal to 90 degree. So theta s will be equal to 45 degree counterclockwise. So if you rotate it to theta s, so you can see here you have negative shear stress in plane shear stress, which is the same result that is shown over here. And that was all about this problem 9-35. I have explained it using both methods. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 9-36. This problem is taken from chapter number 9, that is stress transformation, and book name is Mechanics of Material by R.C. Hibbler. So statement is the square steel plate has a thickness of 0.5 inch and is subjected to edge loading shown. Determine the principal stresses developed in the steel. So you can see this is a square plate, steel plate that is 4 by 4 inch, and this thickness is 0.5 inch, and that is acted upon by edge loading of 16 pound per inch. So you have to determine the principal stresses that is developed in the steel. So we will solve it by using two methods, stress transformation method and by Mohr circle. So you can solve it by any of the one method. So I will solve it by first stress transformation equation. Okay, so you can see this is a edge loading that is given as 16 pound in per inch. So in order to convert it into load, so we will multiply this 6 with this length 4 inch, and that will convert this load into a shear load, which is equal to F Fs, and that Fs will be equal to 16 multiplied by 4, that will be equal to 64 pounds. Clear? So we have this Fs will be equal to 16 pounds per inch multiplied by 4 inch will give you 64 pound. And this is the horizontal shear force. Now to find the shear stress, so shear stress is equal to shear force divided by shearing area. So shear force is 64 pounds and we have shearing area, which is this one. This 4 multiplied by this thickness 0.5. This is the shearing area AS. So I will write 4 multiplied by 0.5 and this will be inch, square inch. And when you simplify it, it will give you 64 divided by this will be equal to 2 and that will give you 32 pound per square inch. Or you can say this shear stress is 32 psi, which is pound per square inch. So this is the shear stress. Okay, so you can see that this is your horizontal axis. Clear? This is your y axis. Clear? So this shear stress will be tau of xy, and this will be tau of xy, this will be tau of yx, and same is the case, this will be tau of y in the direction of x, and this will be tau of xy. Now you can see here we do not have normal stress, so sigma x is equal to 0. We do not have stress in y direction, so sigma y is equal to 0, and we have only shear stress, which is tau of xy, and that is plus 32 psi. So you can see that we will use stress transformation equation for finding the principal stresses. So principal stresses, and principal stresses, we know that principal stress is sigma 1 comma 2 is equal to sigma x plus sigma y divided by 2 plus minus under the root sigma x minus sigma y divided by 2 whole square plus tau of xy square. So just put the value. We do not have 0 plus 0 divided by 2 will be 0, plus minus, same is the case, 0 minus 0 divided by 2 whole square plus 32 square. Clear? That is sigma 1 comma 2. So this will be equal to 0 plus minus 0 plus 32 square, and that will give you plus minus 32 square. So we will get sigma 1 comma 2 principal stresses, sigma 1 comma 2 will be equal to plus minus 32, and the unit will be psi. So it means that sigma 1 is plus 32 psi and sigma 2 is equal to minus 32 psi. So these are the principal stresses that we have calculated, are required principal stresses. Now we will find the location of these principal stresses, that at which angle it will lie or act. So for that we have formula tangent of 2 theta p. Theta p is the plane over which this principal stress acts, and we have this formula tau xy divided by sigma x minus sigma y divided by 2. So put the value 32 divided by 0 minus 0 divided by 2 will be equal to 32 over 0, and we will get infinity. So tangent of 2 theta p is equal to infinity. So from here we will get 2 theta p is equal to tangent of infinity, and by using calculator when you will find it, so you will get 2 theta p will be equal to 90 degree. So it means theta p is equal to 45 degree. So this is theta p1. So this is plus 45, or you can say theta p is also equal to minus 45 degree. So this is theta p2 and this is theta p1. And that is the answer. Now we'll solve this question by using Mohr circle. So again you can see by Mohr circle. So for Mohr circle we need the coordinate sigma x comma tau of xy and another coordinate sigma y comma minus tau of xy. So sigma x is equal to 0 and tau of xy is plus 32 and sigma y is 0 and minus 32. So what we will do is that we will draw a horizontal line or axis as well as vertical axis. Clear? So this is sigma, and here we will plot the on y-axis we plot the vertical. Let each division is of 10. This will be minus 10, minus 20, minus 30. So our first point will be this one. Let this is minus 32. This coordinate is 0 comma minus 32 and this coordinate is 0 comma plus 32. Okay, I will draw it above 0 comma plus 32 and keeping this point O as a center and draw a circle that is passing through these 2 points. You can draw it by using compass. I don't have, so I have to adjust it. Clear? Okay, so you can see that this stress is here. This one will be equal to sigma 1 and this one will be equal to sigma 2, and this this is point A and this is point B. So you can see sigma 1 is equal to OA, which is equal to radius of this circle, and sigma 2 is equal to OB, which is again equal to minus R. So why we will find this R? So R for this Mohr circle is equal to tau of xy, or you can say that not tau of xy, that is sigma x minus sigma y divided by 2 whole square plus tau of xy square. So put the value 0 minus 0 divided by 2 whole square plus 32 square under the root. This will give you R. So R will be equal to 32. So if you put it over here, sigma 1 is equal to plus 32 psi and here sigma 2 is minus R, so minus 32 psi. Okay, and the plane of, you can see this line is define the state, this line defines the state of stress. So for getting the principal planes, so if I take this angle in counterclockwise theta 2, in clockwise or as anti-clockwise, if I take it 2 theta p 2 theta p1, let this is the angle in counterclockwise direction, 2 theta p1, that is equal to 90 degree. So theta p1 will be equal to 45 degree. Or if you want to take this angle that is clockwise, so this is again 2 theta p2. So 2 theta p2 is minus 2 theta p2 is equal to minus 90 degree. So theta p2 is equal to minus 45 degree. And if you want to draw it on a state of stress element, so let me draw it. This is initial x-axis, this is its y-axis, and at angle of 45 degree, let this is 45 counterclockwise theta p1, that is 45 degree over here. and this is your y-axis. Transform y dash x dash y dash, and if you draw the element like this, clear? So what we will get is sigma 1 in this direction is 32 psi. This is theta 1, sigma 1, and sigma 2 is minus 32. So it will be compressive, which is 32 psi, and sigma 1 is plus 32 psi. This is minus. And you can see that by using both methods, you will get the same answer. Sigma 1 is 32 minus, and sigma 2 is minus 32. Here sigma 1 is 32 and minus 32, and these are the principal planes. Clear? And that was all about this problem 9-36. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 9-26. This problem is taken from chapter number 9, Stress Transformation, and the book name is Mechanics of Material by R.C. Hibbler. So statement is the bracket is subjected to a force of 3 kips. Determine the principal stress and maximum in-plane shear stress at point A on the cross-section at section AA. Specify the orientation of this state of stress and show the result on the element. So you can see this is the bracket that is subjected to 3 kips load, tensile load. This cross section at section A is shown over here. You can see this is the breadth, this is the height, and this is the web flange, and this is the web. This is web and this is flange. All the dimensions are mentioned. So you have to find the principal stresses and maximum in plane shear stress at point A, and you have to specify the orientation and state of stress. So let's start with the solution. So when you section it at section AA, so here I have shown, so you will be having a reaction, a normal force that is perpendicular to this surface, and this will be equal to N. Clear? You will be having a shear force as well as you will be having a movement that will be in this direction. Clear? So you will find this V, M and N by using equation of equilibrium. The first equation of equilibrium, that is sum of all forces along y direction must be equal to 0, and upward force is taken as positive. Okay, so you can see only V is acting downward, so minus V is equal to 0. It means that this shear force is equal to 0. Now we'll find this N by using equation of equilibrium, that sum of all forces along x direction must be equal to 0, and force in this direction is taken as positive. So you can see N is in positive direction and this 3 is in negative direction. Their sum must be equal to 0. So from here we will get this N is equal to 3 kip. Now we'll find this moment, and the equation will be sum of all moment about section AA must be equal to 0, and taking the counterclockwise moment as positive. So here you can see this distance from top till this top surface is 3 inch. So this is 3 inch, and this half portion which you can see here, this is 2 inch, so half will be equal to 1. So total distance will be 4 inch. So distance from this till the mid of this is 4 inch. Clear? So you can see a movement about section AA. So this force into perpendicular distance is this one, 4. Clear? And this is producing counterclockwise movement, so it will be positive. The second movement about this section AA is this movement which is clockwise, and that will be negative, but their sum must be equal to 0. So I will write 3 multiplied by 4 minus M is equal to 0. So from here M will be equal to 12 kip into inch. Okay, kip into inch. Now we have all these 3 unknowns. So you can see here that Here we, for normal stress, I will write normal stress, normal stress. For finding normal stress, sigma, that is the combination of this normal load over this face, that will be equal to n divided by a. Clear? And due to this movement in this direction, and due to this movement, it will be in bending stress. So due to bending stress, this will bend like this. The upper portion is in tension while lower is in compression. Clear? So it will be positive plus m into y divided by I. So this n by a is stress due to normal force. Clear? This is the stress, and this stress is due to the stress due to bending moment. Clear? Okay. Now we'll find this A and I, which are the section properties. So section properties, A is the area of this cross section. So you can see this is the cross section. So if I take it like this is the whole area 1/2 inch, and then subtract these two portions. So we will get the area. So area is equal to 2 multiplied by 1 minus, you can see that this height is 2 minus 0.5 minus 0.5, which is 1.5, and this remaining two portions is 1 minus 0.25, which is 0.75. So I will write 0.75 multiply by height, which is 1.5, and when you calculate it, you will get this area comes out to be 0.875 square inch. Now we'll find I, which is the second moment of inertia about this neutral axis, and since this is symmetrical about the center, so we will take moment of inertia I, which is equal to 1/12 its breadth, which is 1, and height is 12. So 1 into not 12, 2 cube. So this will be the moment of inertia when you take this as a rectangular. And now we will subtract the moment of inertia of the remaining these two portions. So I will write minus 1/12. The remaining breadth is 0.75, which you have seen over here, and height is 1.5 cube. So when you calculate it, you will get 0.45573 inch power 4. Now you have all these values, and you can see that we have to find the principal stress at point A. So A is at a distance of 1 from this neutral axis. So Y is equal to 1 inch. So I will write Y is equal to 1 inch for point A. Now you have all the values, you can just put it. N is 3 kips. So 3 divided by area is 0.875 plus moment is 12 kips. So 12 into Y is 1 divided by I is 0.45573. So when you solve this, you will get the stress at point A, which comes out to be 29.76 KSI. So this is the normal stress that is acting at point A. Now for shear stress, we know that shear stress is equal to V into Q, V into QA divided by I into T. So QA will find QA. So QA is equal to Y dash bar into area. Since this is point A, so above this point A there is no area. Area is equal to 0. So it means that QA will be equal to 0. So here then this shear stress will be also 0. Now we will draw the state of stress at point A. Can be represented as, if I draw the element and show the state of stress, so only we have sigma A normal stress in horizontal direction, and that is like this, which is sigma A is equal to 29.76 KSI, and that is also equal to sigma X. There is no stress in Y direction, so it will be 0, and there is no shear stress, so state of stress state of stress at point A. At point A. Now we'll find the principal stresses. So for principal stresses, I will write principal stresses. So here we have sigma x is 29.76 ksi, sigma y is equal to 0, and tau of xy is also 0. So principal stress, you can see that this is sigma 1 comma 2 is equal to sigma x plus sigma y divided by 2 plus minus sigma x minus sigma y divided by 2 whole square plus tau of xy whole square. Okay, so when you put the value sigma 1 comma 2 is 29.76 plus 0 divided by 2 plus minus 29.76 minus 0 divided by 2 whole square plus 0 square. So when you solve this, you will get sigma 1 comma 2 will be equal to 29.76 divided by 2 plus minus 29.76 divided by 2. So from here, if you take plus, sigma 1 will be equal to 29.76 divided by 2 plus 29.76 divided by 2, which is equal to 29.76, and the unit will be KSI. And sigma 2 will be equal to 29.76 divided by 2 minus 29.76 divided by 2, which is equal to 0 KSI. So we will get sigma 1 is 29 point, I will round off it. So this, and sigma 2 is equal to 0 KSI. Now you can also find this sigma 1 and sigma 2 by using Mohr circle. So we will also explain that, like, this is a horizontal axis and this is the vertical axis. On horizontal axis we will take normal stress, on vertical axis we will take the shear stress. So for that we will need the pair sigma x comma tau of xy and sigma y comma tau of minus tau of xy. So 29.76, or you can also say that this is 29.8 comma 0 and 0 comma 0. So if you plot first point 29.08, let 1 division 1, 2, 3, 4, 5 is of 5 KSI. So 5 and this is 30. So 29.8 is approximately 30. So this point will be 29.8 comma 0. And this point will be equal to 0 comma 0. And when you draw a circle which are passing through these 2 points, clear, you have to draw it perfectly. So you will get it like this. Here you can see that this point is sigma 1 and here this is sigma 2. So sigma 2 is 0 and sigma 1 is 29.8 KSI. Now I will represent this principal stress on the state of element R. So this is sigma 1, which is equal to 29.8 KSI, and there is no sigma 2, so it is the only state of stress sigma 1. For in plane shear stress, we have formula maximum in plane shear stress. We have formula tau max in plane is equal to sigma x minus sigma y divided by 2 whole square plus tau of xy square. So put the value, you will get 29.7, 29.8 minus 0 divided by 2 whole square plus 0 whole square under the root. And when you calculate, it will be 14.9 KSI. Okay. Again, you can see that the center of this circle will be equal to sigma average comma 0. This is the center, and sigma average is sigma x plus sigma y divided by 2. So when you calculate it, 29.8 divided by 2 will be again 14.9. Clear? So this point is 14.9 comma 0. Okay, and this is the maximum in plane shearing stress. Here you have sigma, at this point you have sigma average comma tau in plane maximum, and you can see this tau in plane maximum in plane is equal to radius of this circle, and radius of this circle is again can be computed by this formula, which is equal to this. Let me write it: sigma x minus sigma y divided by 2 whole square plus tau of xy square under the root, and you will get the same 14.9 ksi if you use the Mohr circle. Okay, now we will find the orientation of maximum in plane. So for that we have tangent of 2 theta s is equal to minus sigma x minus sigma y divided by 2, clear, divided by tau of x y. So if you put the value minus 29.76 minus 0 divided by 2 divided by 0 will give you infinity. So it means that 2 theta s is equal to tangent inverse infinity. So 2 theta s is equal to 90 degree, and if you want to find theta s, so theta s is equal to 45 degree or minus 45 degree. Clear? Now we'll move toward next page. So we have theta s is equal to 45 and minus 45. So you can, theta s is 45 degree or theta s is equal to minus 45 degree. So put this theta is equal to minus 45 degree in tau of x dash y dash, which is the transform stress when the element is rotated through any angle. So sigma x minus sigma y divided by 2 into sine of 2 theta plus tau of xy cos of 2 theta. So minus 29.8 minus 0 divided by 2 into sine of 90 degree minus 90 because theta is minus 45 plus 0 into cos of minus 90 degree. So when you calculate it, you will get tau of x dash y dash is equal to 14.9 ksi. So this is the positive value, which is maximum in plane shear that occurs at 45 degree shear stress. Now average shearing stress comes out to be sigma x plus sigma y divided by 2. So 29.8 plus 0 divided by 2 will give you 14.9 ksi, and we will represent it on state of element. So let this is your initial x, this is your y, and now angle is minus 45 clockwise. So let this is minus 45 degree clockwise, and this new transform y axis will be y dash will be this. And if you draw the element like this, so this will be the element, clear, and you can see that average shearing stress will be like, it will be like perpendicular to this surface, perpendicular to this surface, perpendicular to this surface, perpendicular to this, and this is sigma average, all are sigma average, and tau of xy is positive, so it will be like our maximum in plane shear stress will be like this one. This is tau in plane maximum. So that was all about this problem 9-26, in which we have calculated the principal stresses, clear, which is sigma 1 comma sigma 2, and we represented it on element and specify the location. Then we discussed the maximum in plane shear stress using normal equation as well as by using Mohr circle, and then we calculated the average normal stress at this angle theta is 45, and specified the state of stress at this theta s, which is minus 45. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 9-27. This problem is exactly the same like problem 9-26, that is taken from chapter number 9, Stress Transformation and Mechanics of Material by R.C. Hibbler is the book name. Statement is the bracket is subjected to the force of 3 kips. Determine the principal stress and maximum in plane shear stress at point B on the cross section at section AA. Specify the orientation of state of stress and show the result on the element. So you can see this is a bracket and this is a 3 kips axial or tensile load is applied. The at section AA, the cross section of this is shown, that is I beam, and you have to find the principal stresses at point B and maximum in plane shear stress, and you have to specify the state of stress and show the result on the element. So in problem 9-26, we solved this. This is exactly the same, but instead of point A, here we will solve it for point B. So let's start with the solution. So first step is that if we section it at section AA and draw the free body diagram, so here at this section we will be having a reaction force which is normal force N, and you will be having a shear force V, clear, and you will be having a moment M. So we'll find this V, M and N by using equation of equilibrium. So first equation of equilibrium is that sum of all forces along y direction must be equal to 0 and force upward is taken as positive. So only V, which is acting downward, is negative and there is no other force. So it means that shear force acting will be equal to 0. Now we'll find this N by using equation of equilibrium, that sum of all forces along x direction must be equal to 0 and force in this direction is taken as positive. So 3 is in opposite direction, so minus 3 plus this N which is in positive direction is equal to 0. So from here we will have N is equal to 3 kip. Now we'll find this moment about section AA. So for that I will apply the equation that sum of all moment about section AA must be equal to 0 and movement in counterclockwise is taken as positive. So here you can see that this is 3. So till the mid of this section, this total distance will be 4 inch. How? Let me show you. This is 4 inch. So this is 3 and this is the cross section. So half of this will be equal to 1 inch. Clear? 1 inch, and 3 plus 1 is equal to 4. So I will write it, this distance is 4 inch. So you can see that this force 3 into perpendicular distance about section AA is 4 and this is producing clockwise, so it will be negative. So I will write it minus 3 multiplied by 4, and this external reaction moment which is clockwise, counterclockwise, this is counter 3 into 4 is producing, this is the force and this is counterclockwise, so it will be positive. So this will be positive and the other one will be negative. So kindly correct it in problem 9-26. Again you will get the same value. Moment will be equal to 12 kips into inch. Now you have this, all these things. So you can see for normal stress, which is equal to sigma, that is the combination of this normal stress that is acting on this surface, and due to this movement and due to this movement, it will produce the bending stress. So this portion will be upward, will be in tensile, and downward will be in compression. Since we are dealing with point B, clear, so this portion will be in compression. It will be taken as negative. So I will write it N by A is the normal stress minus M into Y divided by I. Clear? Now we will find A and I are section properties. So we will find first that section properties. So cross-sectional area of this is can be obtained if we take it as a rectangular box which is 1 by 2 inch, and then subtract these two portion. And these two portion, this height is 1.5 because 2 minus 0.5 minus 0.5 is 1.5, and this remaining two portion is 1 minus 0.5 is 0.75. So I will write it 2 multiplied by 1 minus 0.75 multiplied by 1.5, that will give you 0.875 square inch. And I for this beam is equal to, if I take it as a rectangular box and find the moment of inertia about this axis, so this will be breadth and this will be height. So 1 over 12, B is 1 and H is 2 cube, and then minus these two portion, minus these two portion, and minus 1 over 12, breadth is 0.75 because 1 minus 0.2 will be 0.75, and height is 1.5 cube. And when you solve this, you will get I will be equal to 0.45573 inch power 4. And what about Y? So Y is distance from neutral axis till the point B, and that is 1. Clear? This is 1 inch. So Y is 1 inch. We haven't take minus Y because we already assume that below is the compression. So this is normal stress. So normal stress is N is 3 divided by area 0.875 minus M is 12 into 1. Y is 1 divided by I is 0.45573. And when you solve it, you will get stress at point B will be equal to minus 22.90 KSI. Okay, so this is the normal stress. Clear? And what about shear stress? So we know that shearing stress at point B is equal to V into QB divided by I into T. So this is point B. Clear? So about point B there is no area. So we know that QB is equal to Y dash bar into A. So area A is equal to 0 because there is no area above A. So QB is equal to 0. So it means that shearing stress at point B will be equal to 0. Now if we draw the state of stress element, so it will be like this. If this is the element, clear? This is the element. So only stress in x direction is compressive stress, that is minus sigma B, or sigma x is equal to sigma B is equal to minus 22.90 KSI. Clear? So there is no stress in y direction and there is no shear force, so it will be like this. So here you can see sigma x is equal to minus 22.90 KSI, sigma y is equal to 0, and tau of xy is again equal to 0. So for principal stresses, you can calculate these stresses by using Mohr circle or using this formula sigma 1 comma 2 is equal to sigma x plus sigma y divided by 2 plus minus under the root sigma x minus sigma y divided by 2 whole square plus tau of xy whole square. I have solved problem 12.9-26 by using both method. Here I'm going to solve it by using this formula. So put the value sigma x is minus 22.90 plus 0 divided by 2 plus minus under the root minus 22.90 divided by 2 minus 0 whole square plus 0 square under the root. So when you solve this, you will get sigma 1 will be equal to minus 22.90 divided by 2 plus 22.902 divided by 2, which is equal to 0. And you will get sigma 2 will be equal to minus 22.90 ksi. So these are the principal stresses. So if you want to represent on the element state on element, so representation will be sigma 1 is 0, so it will be like this: sigma 1 is equal to 0, and your sigma 2 will be compressive, that is minus 22.90, and this will be minus sigma 2, which is 22.90. Now we will find the maximum in plane shear stress. Maximum in plane shear stress, which is equal to tau max in plane, and that is equal to sigma x minus sigma y divided by 2 whole square plus tau of xy whole square under the root. So just put the value minus 22.90 divided by 2 minus 0 whole square plus 0 square under the root. So you will get maximum in plane shearing stress comes out to be 11.5 ksi, and we will have average shear stress that will be equal to sigma x plus sigma y divided by 2, and that will be minus 22.90 plus 0 divided by 2 is average normal stress. So, and that when you calculate it, it will be equal to minus 11.5 ksi. Now we are going to find out the orientation of maximum in plane shear. So for that we have formula: tangent of 2 theta s is equal to minus sigma x minus sigma y divided by 2 whole square divided by tau of xy. So minus 22.590 minus 0 divided by 2 whole square. This is not square, okay, remove this, okay, divide by tau of xy, which is 0. So it means tangent of 2 theta s is equal to infinity. So from here t2 theta s is equal to tangent inverse infinity, and we will get theta s will be equal to 2 theta s will be equal to 90 degrees. So theta s is equal to 45 degree or minus 45 degree. So how you will know that what will be the direction of theta s? So put theta s is equal to 45 degree in equation, which is transform equation for shear stress, is equal to minus sigma x minus sigma y divided by 2 into sine of 2 theta plus tau of xy cos of 2 theta. So when you put the value of sigma x, which is equal to minus 22.90, and 2 theta is 2 theta is 90 degrees, so you will get it 11.5 ksi, which is positive. Now if you want to represent it on a state of stress element, so let this is initial axis s x, this was y, clear, and when you rotate it 45 degree counterclockwise, because theta s is positive 45 degree counterclockwise, clear. So your new y dash will be like this, and if you draw the element like this, Clear? So your average shear stress, which is sigma average, is equal to this value, where is 11.5. This will be sigma average. Clear? And your tau of x dash y dash will be 11.5, and this will be in y dash positive direction. I will choose another color. This will be like this will be tau of x dash y dash are maximum in plane shearing stress. This is tau of in plane maximum, or tau of x dash y dash. And this is the representation of state of stress element and specify the location. And that was all about this problem 9-27. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest video. Also share my videos with your friends so that they may also learn and help me in growing my channel. If you have any question, you can ask me in comment section. Thank you for watching.